Hello. So welcome to physics. Welcome to the first lecture on physics, which I've just called Introduction to Physics. And what I'm just going to talk about this lecture is I'm going to talk about, what physics is. I'm going to talk about like an overview, right? So I'll define it, talk about an overview, talk about what it's used for, how it measures things, how it relates to other sciences. Um, in addition, I'll talk a little bit about units that we use in physics, estimation, and things like that. Okay. So the very first thing that we need to talk about, if we're talking about the introduction of physics, is we need to define what physics actually is. So what is physics? It's a good question, right? A lot of people, if you've never had physics before, it would actually be kind of hard to answer this. You may be able to say things like, oh, well, it relates to that Newton guy, or it relates to that thing called, force. Um, Maybe there's energy involved. There's a lot of math involved. There's a lot of equations involved. Um, but what Wikipedia defines this as, and I think it's a really good definition, which is why I usually use it, um, it's considered, so physics is considered the natural science that studies matter and its motion and behavior through space and time, and that studies related entities of energy and force. So let's go over this real quick. So it's considered the natural science, okay, that studies matter and its motion. Okay, so motion is extremely important for us here. A good portion of Physics 1 is concerned with motion and behavior. Okay, we want to be able to track how things are going to move through space as time passes. Okay, and we'll also talk about these related entities of energy and force that kind of allow us to do the same thing. Okay. So in short, that really is what physics is. It doesn't matter what type of physics you're looking at, whether you're looking at, um, what we're doing. We're looking at, things moving typically, or we're looking at, um, you know, pushing on something to make it move. Or if you go on the physics 2 and you're looking at, circuits, you're just looking at a system, the system being some object or system of objects, and you're wanting to know how that moves through time, or through space, and how it interacts with other things around it, its environment. Okay. In short, that's what physics really is. Um, so, like most sciences, because of this, it is a way to understand the universe. It really is, because it's all encompassing. Okay. It's very, very broad. Okay. And you'll see that as we work through this. Um, Once you use physics, or really any science, it can allow you to predict the future. I know that sounds maybe a little cheesy, but it really can, right? If you really think about it, what most science seeks to understand, okay, that we apply through technology and things like that, is that if we study something, okay, we go through, we do the scientific method, and we do everything like that, it allows us to study what's going to happen under certain conditions to certain things. Physics allows us to understand the physical side of that. And so, if I throw a ball and I throw it in a certain way, I can predict what it will do if I should do that again. And so in a sense, it really can allow you to predict the future. And other sciences allow you to do that as well. So what applications can physics have then? Okay, we talked about how it's extremely broad. Most of you who are in this class are not going on to become physicists. A lot of you in here are going on to the medical field or perhaps engineering, depending. And so you must be thinking, well, I'm not going to ever do this. What good is it? Okay, well, to that I say, physics, no matter what you're studying, okay, whatever scientific field or tech you're looking at, physics permeates kind of everything, okay? So it permeates every other science and engineering discipline. So studying it, physics permeates every other science and engineering discipline. So studying it creates a strong foundation for learning other subjects. Okay. Specifically other scientific subjects. And it's true, right? Because I've done physics, I can look at some new technology or something that I've never seen before, and because I understand physics pretty well, I can kind of surmise how that system should work, at least physically. Now, the nitty-gritty details, you have to learn that, right? That's within the science itself. Like, I couldn't just say, okay, I'm going to go be a doctor and understand everything about that within 5 minutes just because I've had physics. But I can surmise how a lot of systems should work on the surface level, okay? Now, the details, that's what you would study the science for, okay? But this does give you a very strong foundation no matter what you do in STEM, and even outside some STEM applications like economics or finance. So the main reason then, the other application this should have, aside from a strong foundation, is learning physics gives you a lot. Here, let's do it this way. Gives you a logical mindset, okay, and problem solving techniques to use in the future. And so this is kind of true, right? So when I teach physics, I do teach physics, but I try to teach it with physics as a backdrop, and I really put at the forefront the skills you gain through physics, the logical mindset. Why do we do things in a certain way? What does that mean? The answer is kind of just what you get at the end. The answer to the problem doesn't really matter in a sense. Obviously, it's how I grade the course. But in a sense, that's not what is important. What's important is the problem-solving technique that you develop, looking at different systems, and the logical mindset that you yourself will develop, okay? So it's super useful. A lot of people think, oh, physics is hard, I just don't want to take it. But it's hard because a lot of people haven't been taught in this particular way on how to address these problems, okay? or certain problems, or a certain way about thinking about something. It's kind of a new way. And so that's kind of why it's difficult in the first place, because it's a new way to think about things that a lot of people haven't been exposed to before. But because of that, it's also extremely useful. So that's the definition of physics and how it's useful. So now let's talk a little bit about more physics itself. So physics covers the study of the physical aspects of the universe and since that is so broad, those studies are divided into 4 main subjects. Okay. So physics covers essentially the physical aspects of the universe. And because the universe is really big and covers also things very small, like on the atomic scale, to do that, we basically ended up dividing it into 4 main subjects. Okay. So here are the 4 main subjects. So the first subject is classical mechanics. Okay, this is the first thing that people think about probably when they think about physics. This is the physics of very slow and large systems. Okay, yeah, it covers. Oops. So this covers very slow as well as large systems. Okay, this would be covered in Physics 1, a little bit in Physics 2, and maybe some biology as well, technically. Okay, there's biophysics. Okay, sometimes biophysics is on the quantum scale, sometimes it's not. It depends on the structures to where these type of rules will apply. But you'll see if you go on in physics or learn new things that slow here means that you're not anywhere near the speed of light. As you approach, or some object approaches the speed of light, the physical entities, the physical systems that define them, we have to basically change the rules a little bit for those types of things, but also large systems as well. So you'll see as you get smaller in the universe, you have new rules that kind of govern you. Okay, new things that start happening. But for Physics 1 and stuff, we can use these classical mechanics rules that we'll talk about for the bulk of the lecture, okay, or the bulk of the class. So this will be pretty much everything we do in here. The next thing that you would perhaps study in physics is quantum mechanics, like if you were to go on. So this covers very, again, slow things, so still not anywhere near the speed of light, but this time it's small. Small systems. Okay. So these would be things on the atomic scale, okay, and systems on the smaller scale. So the type of physics you would cover with this are, again, it's called like atomic molecular physics, where you're looking at single atoms or maybe molecules, very simple systems of molecules, and understanding how they move, how they interact with other things around them, their environment. This consists of solid state physics, where this is basically like semiconductors or can be semiconductors. These are different materials and how, say, electrons move through those materials. There's also quantum biology. Perhaps some chemistry would fall under this. You'll see as you study some higher level sciences, if you take a lot of sciences up, you'll learn that they're very interdisciplinary. So I know in my work, even though I did stuff in solid state physics, for example, we had to cross over, and a lot of the work was done in chemistry and things like that. Okay. So the third thing that physics is split up to, the third subject, okay, is called relativistic mechanics. Okay. These are things that are very fast, okay? So again, this means it would be approaching the speed of light. You know, maybe it's 30% of the speed of light or whatever. And also very large things. So R scale, not quantum mechanics scale. And if you're studying this stuff, you're studying special relativity, okay? This is actually, special relativity is actually very valid in our everyday lives because we use it for things like satellites, where you're adjusting their internal clocks, kind of things like that. Space travel would be relevant here, where we need to start looking at that, because it turns out as you move fast, even if you're a large system, things change. You get time dilation, length contraction, things like that. And you can also get some apparent paradoxes that aren't really paradoxes. But yeah, if you go on in physics, again, this would be something you study, at least a little bit, in undergrad. So the last thing that physics is split up to is relativistic quantum mechanics. So you can kind of see these are divided up based on how fast you're going and your size. So this would be fast and small. Okay. And essentially this covers particle physics, okay, which kind of examines, you've got two particles colliding in, like, say, the Large Hadron Collider or things like that, and they collide, and then a bunch of particles spit out, okay, based on that collision, and they spit out at different angles and things like that. So this allows us to study our the fundamental building blocks of our universe, okay? What type of particles really make up our entire universe? And there's quite a bit, right? It's not just protons, neutrons, and electrons. There's a lot more than that. And particle physics kind of helps you study that. So the next thing we need to look at, so that's basically how physics is split up. And the next thing we want to talk about is units, okay? So whenever units are important, because whatever it is you're talking about, you need to discuss it with certainty. You can't just say, oh, that's kind of big, right? You need to be more certain about that. And this is further kind of complicated, this whole setup of units is further complicated by the fact that physics, as you just saw, ranges from very small things to very incredibly large things. And so because of that, there needed to be a system of units in place that makes sense, okay? So what people developed over the years is the international system of units, okay? So ability to study the universe from the tiniest particle to something as large as the observable universe, which is the range of the universe that we can observe. Okay, it's based on light speed and time. It's not the size of the universe, it's just what we can observe around us. But it's very, very massive. And this requires a set of units that are scalable. Okay, these are the international So this is, let's just do that. So this is the international, can't write, save my life. The international system of units, or SI units is what they're known as in short. Okay. So these are the SI units. Okay. And these units are comprised of 7 base units with other units that can be derived from these. Okay, so there's 7 base units that can be used to discuss basically anything from the very tiniest particle to the largest particle if you use those base units and mix them up and combine them a bit. Okay, so here's how it's split up. So you've got something called a dimension, which is just considered a base unit without the unit attached. It's just what you're measuring without a thing attached. For example, if you wanted to measure the length of something, okay, the length is the dimension, but the unit you're using may be foot, inches, whatever. Okay. So how I'll write this is I'm going to set up a table, and I'm going to write the dimension, then the symbol for that dimension. Then I'll talk about what the SI unit is for that. Okay. And this is what they're defined by. Okay. And this would be currently. Okay. Although some of them have been changing recently. Oops. I can get somewhat of a straight line here. Okay. So you've got length. The symbol for that is just an L. Pretty simple. The unit that we'll use, the SI unit that we'll use for that, okay, is the meter. And this is defined actually in terms of the speed of light. So what you'll see is most of these definitions are constants of nature, okay, or constants of the universe. They're not based on, say, the length of my hand or the length of, like, from elbow to tip of the finger, right, like they used to be. They're based on something that's not changing, like the speed of light. Okay. So the meter is defined in terms of the speed of light, which is a constant. That way, when we discuss what a meter is, it won't change, right? A meter to me is a meter to you, is a meter to anyone else reading the scientific paper or article or whatever. That way, there's no confusion, no ambiguity. Instead of kind of large, it's 1.2 meters long. So the mass is defined in terms of the kilogram. Okay, we'll talk about what mass is and everything like that. And this used to be defined actually in terms of, so it used to be a cylinder that I believe was located in France, I think. But now it's something different. It's defined in terms of the Planck constant. So now the Planck. And you'll see this if you get into quantum mechanics, but essentially the Planck constant is a constant that's defined in terms of energy. And energy is kind of mass in a way. So I know it's a little confusing, so you don't have to worry about it. But it is defined in terms of a constant in nature, just how much a kilogram is, right? And they recently did that, I think like last year, 2019. So time is defined in terms of the second. The symbol for that is S. The symbol for kilogram, sorry, was kg. And this is actually basically the cesium atom is how the second is defined. So the cesium atom rotates between or cycles between states at a certain frequency, and so many of those cycles is considered 1 second. So you'll see length, mass, and time. This is what we do in Physics 1. We'll pretty much use these exclusively. Length, mass, and time. If you go on into Physics 2, you'll use this next dimension, which is electric current with the symbol I. The unit for this is the ampere, big A. And this is actually defined in biparallel conductors. So essentially, what current is just the flow of an electron, and how much of these electrons flow at a certain rate in between these two conductors that are a certain amount apart defines what the ampere is. Okay. Didn't mean to zoom out there. There's thermodynamic temperature. And this is actually the symbol, sorry, can't do, is actually capital theta is what this is. And if you add 2 eyes to it, it looks like a face. I think that's kind of amusing, actually. But thermodynamic temperature, this is the Kelvin. And I believe this is defined in terms of the triple point of water. And if you don't know what the triple point of water is, it's essentially any state that exists in, solid, liquid, gas. It's where it exists at the right temperature and pressure to make it be all 3 states of matter at once. Okay, and it's defined in terms of that. Pretty sure. There's also amount of substance, which is N, okay, for the symbol, and this is the mole, okay. So these two, thermodynamic temperature and amount of substance, you would get if you took chemistry or take chemistry, okay. And this is in terms of carbon-12 atoms, okay. Some amount of them is considered a mole. The last one, okay, you must be thinking, well, we've done 6. I can't really think, what would the last one even be? And this is actually luminous intensity, okay, which is the symbol J. The unit for that is actually a candela, which is the unit CD, okay. And this is radiation. It's defined in terms of radiation intensity. So this luminous intensity is used to measure how luminous stars are or other objects in our universe, okay? So you would use that if you're studying astronomy or astrophysics, okay? So the ones we are going to focus on in this course, so is length, mass, and time. The others are physics, chemistry, and astronomy. Okay. So these 7 quantities can actually use to be described anything in the universe. So or 7 dimensions. Can be used to describe anything in the universe. Okay. You put them together and you'll see all the units that we use in this class are all derived from length, mass, and time. Okay. Or they're those units by themselves. Okay. So that said, oops, that said. Other units obviously exist. But we stick to these, and the reason that you use these units in the first place, because they are scalable. So that's what I said before, right? You're trying to, right here, scalable, right? You're trying to study things that are large and small. They need to be easily scalable. Easily, okay? Otherwise, there's no point in using them. So there's a prefix system for this. There's a prefix system. To make these units scalable, okay? And I'm going to go through and do it by order of magnitude. So we'll talk about the prefix, the symbol for that prefix, the factor that it is, how big it is, and then the power. So if you were to do scientific power for it, I need to actually probably spread these out a bit. I have the space, I might as well use it. Okay. So let's do my terrible straight lines again. So the first, and we're going from kind of large down to neutral, down to small. So giga is the first one. The symbol's G. The factor of this is actually 1 billion. 1, 2, 3. 1, 2, 3. 1, 2, 3. And the power for this means 10 to the 9. So if you put gigameter, that means 10 to the 9 meters. Okay? And that means 1 billion meters. Okay, so mega is the next one. Big M. 1, 2, 3. 1, 2, 3. So since there's 6 zeros, we put a 6 right here for the power. So that means a megameter would be 1 million meters. Okay. We don't really use giga or mega too much. They're kind of there just to make for a complete table. So kilo, we use a lot. So kilo is a K. And this is just 1,000. And this is 10 to the 3. So kilometer, 10 to the 3 meters, or 1,000 meters. You have hecto, which we don't really use. Again, this is for completion really, but it's an H. And it's 100, so this would be 10 to the 2, so a hectometer. Okay. Then you have your base, which is none. none. This is just your base, so this would just be 1 or 10 to the 0, okay? So this would be, you just wouldn't put a prefix if you wanted to say 1 meter, okay? You would just say a meter, you wouldn't put any prefix there. The next one on the list is centi, so now we're getting below 1, okay? And this is a C, and this is 0.01, so now we're going to the right 2. So it'd be, since it's smaller, it'd be 10 to the minus 2, 1, 2, okay? And so a centimeter would be 10 to the minus 2 meters, or 0.01 meters. Okay. See how that works? You've got milli, which is m, 0.001, and this would be 10 to the minus 3 meters, or 0.001 meters. And these, centi, milli, and kilo, these are the ones we mostly use here in this class. But there are a couple others. There's micrometer, okay? This one uses this fancy looking U, and it's actually called a mu, kind of like the Pokemon, Mew. And this would be 1, 2, 3, 1, 2, 1. So 1, 2, 3, 4, 5, 6, 10 to the minus 6 meters. So a micrometer. And the final one on our list would be nano, and this would be, you can kind of guess, 1, 2, 3, 1, 2, 3, 1, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the minus 9, so a nanometer, okay? Nanometer, pretty small. You're talking about this stuff, you're talking about like semiconductors, you know, like how they're manufacturing certain like CPUs or whatever, they're doing it on a 14 nanometer process, a 10 nanometer process, you know, and that's like only so many silicon atoms wide, so it's extremely small, okay? So that's how we kind of expand and make use of our base units, make them scalable. Another thing, one last thing you can do with units and dimensions is determine relationships or equations between quantities. So for example, say you're taking an exam in this class and you don't know what the equation is and you can't figure out what the equation is. You can actually use what's known as dimensional analysis. So this is, you know, a form of dimensional analysis that you're probably familiar with in chemistry. This one's a little bit different, to determine that, okay? And you'll see when we do examples, we'll do that kind of stuff. So far, here's our roadmap. We've talked about what physics is. We've talked about applications of physics. We've talked about the types of physics you can study and what some fields that they cover, you know, very interdisciplinary. And then we talked about the units that allow us to do that. So now let's, one last thing that they discuss in most intro physics books, and yours as well, I believe, is the scientific method of it. So a large part of any science is the scientific method. This is how, you know, science makes progress, okay? Is through this method, right? And physics is no exception to this, okay? None. Physics has a scientific method as well. There's, you know, there's observation, right? You're observing something happening. There's hypothesis, coming up with reasons, okay, that it could be happening. You're predicting, testing, analysis, and, uh, you know, even some luck every once in a while. That's not an official step, but there's definitely been a lot of scientific discoveries from this. So, you know, there's been quite a few, right? In all fields. That if it weren't for some luck, we wouldn't have discovered it at that moment in time because we didn't know it existed. So, so the scientific method allows us to discuss various observations and studies in the universe. That said, we still need one more system to accurately do this. Okay, so let's think about this. You just do the study. Okay, you've observed, you've had several hypotheses, predictions, tests, blah blah blah. That all means nothing without telling your audience about the error. Okay, so that brings us to error. Every measurement and every measurement device has an error associated with it. And we'll talk about this more in the lab portion of the course, okay? It's vital to discuss that error with your audience, okay? Now I said we'll talk about this in the lab course. That's because in the lecture part of the course, what we're doing now, we do theoretical problems, right? But with the lab portion, you'll see we're making measurements, and so we need to discuss what our data means with error attached so that it actually means something, okay? Error can be represented as an uncertainty, okay? Which, so a number or percentage. Like for example, I measured the speed of light plus or minus 10% on my measurement. A 10% variance is large, but you're being honest, right? But you can also use a number with that, right? Plus or minus 1,000 meters per second, right, on your value. And I'll talk about how to do that when we do some problems, okay? So there's another thing with error, sig figs, okay? So let's talk about sig figs just a little bit. Why are they important? So sig figs, significant figures, okay? Or sig figs. These are important because they allow us to not report values that are more accurate than we know from the device, okay? So for example, if I measure something with a ruler, and that ruler only has, you know, it's down to the millimeter. If I say I know the length of something, 0.000001 meter accuracy, that would just be incorrect, right? Because I can't actually measure that small. And in the lab, we'll talk about a little bit about what devices have what sig figs associated with them and what uncertainty associated with them. It's based on the measurement device that you're talking about, so it varies. In problems, so in general, in problems, you the value with the least number of sig figs is or determines the overall accuracy of the problem or of the experiment, okay? So what this means is if I measure, like I want to measure maybe the area of my desk, and I measure it with 1 millimeter accuracy on one side and then 1 centimeter accuracy on the other side. I can't say I know the area of that with millimeter accuracy because I measured another side with centimeter accuracy, which is less accurate. Okay, so the least accurate thing determines the overall accuracy of the experiment. So that's another way to say that. Least accurate measurement or value determines overall accuracy. Okay, and in turn, overall sig figs. Okay, and we'll talk about how to do that. So that said, here are the specific sig fig rules. So that's generally, like if you're in a pinch and you don't know how many sig figs, how accurate you are, you can use that. But here are specific sig fig rules, okay? Number one, there's only 4. So non-zeros, and if you've been in other scientific courses, you've probably heard this a lot, or math. So non-zeros, they're always significant. So if there's 1, 12, that would be 2 sig figs. Okay, and we'll do examples. We'll do examples with these sig figs so you know what's up. Any zeros between non-zeros are significant. Okay, so 1,001, because it's between those two, that would make those significant. Trailing zeros are not, unless past, how do I say that? Unless in decimal portion. So for example, 1,000 would only have 1 sig fig. If you do 1,000 period, that period implies you know with accuracy that number, and so that makes those 3 significant. Those 3 other zeros significant, and that would be 4 sig figs for that, 1,000 period 4. But again, we'll do this. And again, here's the last rule. Use least sig fig for math. So like addition, etc. Okay, you want to use the least significant figure. One last thing with experiments. The difference between accuracy and precise. I will use this. So this is like a really bad bullseye or a really bad dartboard. Okay. This is where they land. This is precise. They nail the same spot repeatedly. Okay. They can hit the same values each time, no matter when they do the experiment. Okay. You also have this next one. This is where they land. This is accurate or accuracy. They hit the bullseye close to known values. Okay, so that's the difference between accuracy and precise. Okay, a lot of people get those confused. So, yeah. There's one last thing. In physics or in science in general, so if an experiment or problem cannot be done. Estimation can be used. Okay. And so this is when you kind of these are quick these are quick calculations. Like maybe you're like the pool is about that size. Or the book is that big. Okay, so like you would say, the book is and you must be thinking, well, how do I estimate? How do I do that? If you know about the size of like a typical page and you know how many pages there are, you can quickly multiply, right? If you know maybe how much water is in the pool, maybe you can figure out the volume of the pool. Okay. So that's pretty much it with the intro stuff for physics. So we talked about what physics is, what it's used for. We talked about units, and we talked about estimation, accuracy, precise, and of course significant figures. And all of these last things are about experiment, okay, which is extremely important in any science and physics as well. And then of course estimation. If you don't have time or you can't do a problem really quick, you can do a quick estimation. These aren't meant to be accurate values by any means, but they're meant to just give you a quick idea of what's going on. So a quick judgment to the system can be made. Anyway, I will see you in the next one. Thanks for watching.